In talking about process variability, we really first need to look at several components of it. The first one has to do with specification limits. There's an upper specification limit, or USL, and a lower specification limit, or LSL. These specifications are set by the design engineers, the people that design the parts, and they say in order for everything to fit together, these must be the specifications. And there's a variation. They'll say between 1 inch and 1.2 inches is the length of this thing, for example. Now, sometimes the machinery used to make the parts cannot meet the engineering specifications, or lower and upper specification limits. So here's a situation where, again, here's the upper specification limit. Any parts that go beyond this limit are considered to be defective. Any parts that go below this limit are considered to be defective. And of course, this dashed line is the center of specifications, which is where we want our part variation to be centered on, if at all possible. So when we look at parts, let's say that we took measurements of 50 parts in a 10-minute period. And we measured the parts and found that they ranged anywhere from this value to this value, all the way in between. So there's a variation, natural variation in the parts. So this bell-shaped curve represents the amount of variation in a given period of time of a number of parts that were measured. So which processes are not centered? Centering only has to do with where the middle point is with respect to this dashed line. So this one is centered. I don't care whether or not the tails fit within the white zone, as long as this center is centered. This one is not centered. We are making 50%, which is half the area under this curve, bad product. This one is better, but it's still not centered. It's below. It should be right here. And we're making, maybe 10% bad product. This one is even worse. We're probably making 70, 80% defective product. Again, all that we are really looking at is, for this part of it, is where the center line is. Which processes are producing defective parts? What approximate percent? I've talked about that. This one, we are making essentially no defective product. This one is making 50%. This one's probably 10%. And when I'm coming up with these numbers, I'm saying this area with regard to this area, what's that ratio? This one, again, I said was 70, 80%, something like that. You know it's going to be over 50 because this one is 50 right at the halfway point. The next question, which processes have too much process variability? When I'm asking this question, I am not asking where the center of the bell-shaped curve is. This one is centered nicely. This one's centered nicely. This one is a little bit low. But I'm not looking at that when we're talking about process variability. Process variability has to do with the distance from here to here with regard to the engineering specification limits. So this one is just about the maximum width it can be as far as process variability, because this tail to this tail is the same as the specification limits. This one you say, oh, this is bad, but it's really not, because again, for variability, it's just this distance to this distance. If we look at this distance compared to this distance, this is not as wide as this, so the process variability is fine. It's just where it is centered is the problem. This one, how does this distance compare with this distance? This distance is wider than this distance, so there is too much process variability. Same thing with this one. This distance to this distance as compared to this distance is too wide. Of course, it also has an average problem as well. Even if it was centered, the tails would still exceed this distance. I do want to point out you can't make parts exactly the same because variability always exists. You may have little differences in the material. You may have a machine that doesn't make parts exactly the same every time. Even temperature of the building could change and impact the variability. So let's take the next step in the process and look at processes that are not centered and may have too much variability. In the following illustration, ignore all distributions but the one in question. We're going to look at them in isolation. Describe if it is centered, if it's too variable, and if you're making defective product. So, first one, centered. Does this line up with this? No, it is not centered. Variability, is it too variable? This distance is smaller than the engineering specifications, so the variability is acceptable. Is it making defective product? There is nothing hanging below or above the specification limits, so it is not making defective product. B, is it centered? No. This is not there. It is not centered. Is it too variable? Is this distance greater than this distance? And the answer is no. It is not too variable. Is it making defective product? Yes, because some of the line exceeds above the upper engineering specification limits. C, is it centered? No, this should be here. Is the variability too great? The distance from here to here is greater than the distance from here to here, so there is too much variability. Is it making defective product? Not here, but definitely down here because the tail goes beyond the lower engineering specification limit. D, is it centered? Yes, it's right there. This is right there. Is it too variable? This distance is greater than this distance, too variable. Is it making defective product? Yes, it's making defective product here, and it's making defective product there. E, is it centered? Yes. Is it too variable? No. This distance is no more than this distance. It could be exactly the same, I should point out, but it is not greater. Is it making defective product? No. There is no part of the tail that exceeds the upper or lower specification limit. In the last section, we treated each bell-shaped curve as an isolated incident. In this case, we're treating them as this occurred at 8 o'clock in the morning. Let's say this occurred at 10 o'clock, 12, and 2 o'clock, for example. And we're looking how the process changes over time. Remember, we have upper specification limits, engineering specifications, lower specification limits. So what's happening here? Well, it looks like our average is shifting, which means our process average is shifting upward over time. If I look at variability, it's pretty consistent across the day. So are we making defective product? Not yet, but it certainly looks like we're headed that way in the next round. In this one, it looks like the average is shifting up, and then all of a sudden it drops, and then it starts shifting up again. What may be happening here is the person running the machine may make an adjustment and bring the average down to here, and then it starts creeping up like it does. It could just be a function of the machine. The drill bit is getting worn as the day goes on, and then they change it out, put a new drill bit in, and it operates like this, for example. Let's take a look at this one. The average is pretty consistent over time. It's not where we want it to, but the variability still looks good, and we're not making defective products yet. And then at this particular point in time, the average shifts up, but the variability increases, and it's consistently bigger than these. So it appears that we are not making defective product at all during this time sequence. However, the variability has increased even though the average has improved. This particular time sequence of like 8 o'clock, 10 o'clock, 12 o'clock, 2 o'clock, 4 o'clock, 6 o'clock, etc. You have this process here, the average is here, it jumps up to there, it jumps down to there, it jumps up to there, it jumps down to there, up, down. The average is unpredictable. We don't really see a pattern here. In looking at the variation over time, the variation is okay, it gets bigger, it goes down, it kind of stays the same, it gets bigger, it stays about the same, it gets smaller, it gets bigger. It's unpredictable too. This process is unpredictable, and we would even go so far to say is out of control. We don't really know what's going to happen next.